All right. Hello, everyone. I'm excited to kick off this webinar today. My name is Valerio, and I'm an applied science manager at Amazon Web Services. We are going to talk today about how to optimize the accuracy of your machine learning models with advanced hyperparameter tuning in Amazon SageMaker. I'm going to present together with Olivier and Thomas. So, Olivier, you may want to start with a quick introduction.
Hello, everybody. I'm Olivier, calling from France, and I'm a machine learning specialist solution architect at AWS, where I've been for 5 years, at Amazon for just over 8 years. And so I help customers do ML on AWS, and that includes enabling them to tune and optimize their models, typically with SageMaker model tuning that we will cover today. And with that, I will let Thomas introduce himself.
Thank you. Hello, everyone. My name is Tamás Vörös, and I am a senior data scientist with the Sophos AI team. I have been with Sophos for 6 years now. Thank you.
Thank you, Thomas, and thank you, Olivier. I'm going to kick this off, and then Olivier will continue with the demo of SageMaker automatic model tuning, and Thomas will show how to use it for a business use case at Sophos. So let's get started. Let's look into how you can tune your machine learning models to the highest accuracy with advanced hyperparameter tuning. So let's look at the brief agenda for today. We're going to start by what is hyperparameter tuning and why is it difficult, how to find the optimal hyperparameters for your machine learning models, and then the benefits of tuning your machine learning models in Amazon SageMaker automatic model tuning. As mentioned, we are going to continue with a demo from Olivier and a customer spotlight from Sophos, how you use automatic model tuning at Sophos for Sophos business use cases. And we're going to finish with the Q&A. So let's start with a typical machine learning problem. Suppose you have a model, any machine learning model, for example, a neural network, and you want to optimize this neural network for optimal performance. Now, the problem is that you typically have a very large number of hyperparameters. You have the architecture hyperparameters, how to set the number of hidden layers, activation functions, or the model complexity, how to set the regularization level, the dropout rate, or even the optimization parameters, the learning rate, the momentum, the batch size of SGD. All these hyperparameters need to be set somehow. They are not learned by the model, so you need to do it with hyperparameter tuning. What is hyperparameter tuning? We looked at the neural network problem, but this is actually very general. If you have a decision tree model, you also need to tweak manually what is the tree depth, what is the max number of leaf nodes. But really, any arbitrary tasks doesn't have to be a machine learning model. Whenever you have an experiment and you have some knobs to tweak to optimize your objective metric, then you need hyperparameter tuning. For example, you want to optimize download speed and you have some configurations to achieve that. This is a hyperparameter tuning problem. You have some knobs to tweak to optimize your objective. We are going to see how you can tune your hyperparameters in all these settings efficiently. How to find the optimal hyperparameters. How people do this typically, practitioners do this, is through grid search. So what you do is, suppose you only have 2 knobs to tweak, 2 hyperparameters. Then you want to try different combinations of these hyperparameters as in a grid. Each point in the grid corresponds to a different hyperparameter configuration. And then after trying all these hyperparameters as in a grid, you pick the one that optimizes your performance. For example, optimizes your accuracy. Now, the problem with grid search, which I just described, is that it's very expensive. And it's also suboptimal because suppose you have 2 different hyperparameters that you want to tweak to optimize your performance. One is completely irrelevant for performance and the other one is important. Now, the problem is that you're trying many different combinations, in this case, 3 different combinations of the irrelevant hyperparameters while keeping the important hyperparameter fixed. This is not giving you extra information. So a better way to do this is through random search. Random search on the right-hand side, it's simply picking hyperparameters at random from your search space. You can see how the black dots, each black dot is a different hyperparameter evaluation, are now uniformly at random picked from the space. The advantage is that you're not trying many times the same configuration of the important hyperparameter. So you're exploring the search space more effectively and you are leading your search to find a better optimum. But can we do better than this? Can we do better than random or grid search? And this is what we do in Amazon SageMaker Automatic Model Tuning. On top of offering random search, we also offer Bayesian optimization. What's the idea of Bayesian optimization, and how can you use that to optimize the accuracy of your machine learning models? It's called Bayesian because instead of just trying hyperparameters at random, as we just seen, you can now use the information that you learned from the current evaluations to decide what is the best hyperparameter that I should try next. It's called Bayesian optimization because you update your prior knowledge about what is a good hyperparameter into a posterior knowledge. This helps you make your search more effective and efficient. More formally, our goal is to minimize some function f. For example, you want to minimize your validation error on your validation dataset, and you want to find the optimal hyperparameters to achieve this. The optimal hyperparameters may be the number of trees, the number of nodes in an XGBoost model. Now, the surface in the plot is our objective function, say our error on the validation set that we want to minimize. The problem is that this is not a trivial problem. F of x, our function, our validation error, may be very expensive to evaluate. Every time you want to know how well this hyperparameter configuration performs, you need to train a model. You may need to train a neural network model, for example, which may take hours or days to do. Now, the problem is that you don't have an analytical form or gradient for f of x. You cannot just use stochastic gradient descent to optimize that. You need to do it with some sort of trial and error. And on top of all of that, evaluations may be noisy. When you try the same hyperparameter configuration twice, you may not necessarily get the exact same result because your algorithm may be stochastic. All these challenges are overcome through Bayesian optimization. So how does this work, and how can you use Bayesian optimization to optimize your models? There are two main ingredients, which I'm going to look into more detail in a second. There is a model and there is an acquisition function. The model is used to learn what is the relationship between the hyperparameters and your objective metric. For example, the model will tell you what are the most promising regions of the space that should be explored, what regions of the hyperparameter space are likely to give me a good accuracy. On the other hand, there is an acquisition function. Now that we have a model that tells us the relationship between the hyperparameters and the objective function, the acquisition function is telling us what is the best next step, what is the best next hyperparameter that I should pick to optimize my objective metric. Let's look at this with a picture. So on the top side of the picture, we have a true function that we want to minimize. So on the x-axis, we have a single hyperparameter. We have one knob that we need to tweak to optimize our performance. On the y-axis, it is our objective. For example, the error that we want to minimize, the validation error. Now we want to find the optimal point, the optimal hyperparameter that minimizes our error. The true function that we want to minimize is the dashed red curve. And then we have a model for this function. The model is the black curve. Ideally, our model should be as close as possible to the red curve because we want to learn what is the minimum, what is the hyperparameter that is minimizing our function. However, we only have two black dots, two hyperparameter evaluations at the beginning of our search. So our model will be quite accurate at those 2 points, but it's very uncertain everywhere else. The uncertainty is represented by the gray shaded area. Now we have a model, and we want to know what is the next hyperparameter, the next black dot that I should be picking to minimize my error. This is why we have an acquisition function. The acquisition function tells us that we should try out this hyperparameter here on the left because we are very uncertain about what is the true objective at that point. You can see the shaded gray area is very large. So it means that we may be lucky. We may find a good solution there. So we try that next. We evaluate that hyperparameter and we update our Bayesian model. So now the black curve is more certain that at that point on the left, we have that objective function. We continue iterating these two steps. Our acquisition function tells us what we should try next, and then we evaluate that hyperparameter. We train the model with that hyperparameter, we compute the objective, and now we can update our model. You can see how, iterating these steps, the black curve gets closer and closer to the red curve, which is the true objective that we want to minimize. We iterate these steps. We get closer and closer to knowing the true objective, and up to the point where in this picture, you can see how the black curve, our model, our Bayesian model, is very similar to the red curve. So we have a pretty good understanding of where our function is minimized. So we are in the position to say that this hyperparameter configuration is the one that minimizes our objective. And this is the one that you should use to have the lowest error, the lowest validation error. Now, all of this smart logic to find hyperparameters efficiently is offered through Amazon SageMaker automatic model tuning, which you can use to automatically tune the hyperparameters of your algorithms, either through random search or also Bayesian search. The advantage of SageMaker automatic model tuning is that you can tune your models at scale. You can adjust and try out up to thousands of different combinations of hyperparameter configurations. It is intelligent because it uses machine learning to find the best hyperparameters. It is faster because you don't have to do manual search, which is very tedious and may take days or weeks for you to find the optimal hyperparameter configuration. And then it's also production ready. So it's a serverless managed online service. It's not just a library for hyperparameter tuning. It's a service with a stable API, which you can quickly use to optimize your models. Let's now take a look at how this works behind the scenes from a technical perspective within SageMaker. We have looked at our Bayesian optimizer. Our Bayesian optimizer will be responsible for finding the best model for you. So you start a tuning job, and then the Bayesian optimizer will try out many different configurations of your model with many different hyperparameters. Now, every time a different hyperparameter needs to be evaluated to see how well it performs, you need to train the model. So automatic model tuning will automatically do this for you on an EC2 instance. So it will launch many different training jobs on different EC2 instance clusters so as to evaluate how that hyperparameter configuration performs. Each EC2 instance will be a model trained with a different hyperparameter setting, and then it will return the best one for you. Now, one may wonder, what does the difference between Bayesian search and random search look like in practice? So let's look at this with a picture. Suppose you have a tree-based model that you're trying to optimize for accuracy, and you have two different hyperparameters that you can tweak, lambda and alpha learning rate. If we compare random search and Bayesian search based on what hyperparameters are recommended by the search, on the left-hand side, you can see that random search is taking points uniformly at random from the space. Each dot is a different hyperparameter configuration, a different combination of lambda and alpha. On the other hand, Bayesian search is not doing this. It is focusing on a specific region of the space in the bottom left corner, because Bayesian search understands that that's the most promising region of your space. So it's worthwhile trying out more hyperparameter combinations in that space. For you, this means that you will save time because you will not need as many trials to find the best solution. We can also look at this from a different angle. What is the speed of convergence of Bayesian search versus random search? Here in this plot, we compare the two strategies versus the number of training jobs. How many hyperparameter evaluations are required to get to some loss function, which is the y-axis. Again, here we want to minimize our loss function. When we compare the two, you can see how Bayesian search is faster at finding a good loss function, a better minimum compared to random search. So for the same number of evaluations, you find a better solution, which means that you are faster at finding your optimal model. We recently launched in SageMaker automatic model tuning a third search strategy on top of random search and Bayesian search. This is Hyperband. Hyperband is another search strategy which makes the following improvement. When you have many different hyperparameter evaluations, you may not need necessarily to train each one to full completion. For example, you try out a different neural network architecture, and that requires a training loop, but that training loop may be very expensive. So you may want to early stop some of these configurations so that you save time. And this is all handled automatically through Hyperband. So many of these training jobs, each one with a different hyperparameter configuration, it will be early stopped. So it will save resources and focus on the most promising hyperparameters. Let's look at what's the impact of this. If we consider a computer vision problem, tuning a ResNet 20 architecture, comparing random search and Hyperband in terms of walk log time to find the best test accuracy, you can see that the orange curve, Hyperband, it's much faster at finding some level of test accuracy compared to random search. When we look at what random search finds in 10,000 seconds, Hyperband already found it in 2,000 seconds, which is a 5x improvement of your runtime. Now we have seen how hyperparameter tuning works, how you can use different search strategies to optimize your models. The next question is, how do I set up a hyperparameter tuning job in Amazon SageMaker automatic model tuning? There are three main ingredients. You need to specify what is your objective metric, what are the hyperparameters, the knobs that you want to tweak to maximize your objective or minimize your objective metric, and then some job configurations. And that's all you need to kick off your job. We are going to now look at this more precisely, and I'm going to hand it over to Olivier, who is going to show us a demo of how to use SageMaker automatic model tuning for a business use case. So Olivier, please feel free to take it from here.
Excellent. So I am here in a SageMaker Studio, which is the managed notebook service and IDE of Amazon SageMaker. And so I have I'll be using an example slightly derived from a public example we did at reInvent 3 years ago, actually, the dice counting with YOLO 3. You can check out the link on GitHub with that QR code. And to tailor a bit the demo to our use case of today, I just adjusted the version to MXNet 1.6 to have good convergence. And I also removed sections on Neo compilation about ground truth data annotation, which were a bit out of topic for today. But otherwise, the code is pretty much the same. This content is on GitHub. And so basically, to illustrate use case for SageMaker model tuning, we're going to take a use case of a custom Python script, and in particular of a computer vision object detection training loop. And so this is a pretty standard code, basically a training loop. So this one is written in Apache MXNet imperative deep learning framework, pretty similar to PyTorch in terms of formalism. And I'm going to show how we can tune the parameters of our choice to optimize the objective metric of our choice in a fast and efficient fashion with SageMaker model tuning. So I have a couple of imports in the beginning that I run already, so I'm not going to run them again. What I wanted to show is the data. And so typically here we have, I think 300 or so, 315 pictures. Let's see what the data set looks like. So it's basically pictures of dices. And yes, so the goal is to train a model that can isolate those dices, that can, crop, make bounding boxes, and assign a label as well, a class from 1 to 6 of what number we have on the dice. And so this use case itself, I don't know if it's actually useful to specific vertical, but this pattern of object detection is pretty frequent, and we see many customers use object detection for a variety of actual use case. So this could be, in an autonomous vehicle to perceive the road and the landscapes. Could be also in agriculture for aerial imagery analysis. So object detection is very frequent use case. It's very compute intensive, both for training and for inference. And yeah, so it's important to tune those models. And there are many things to tune. Typically in this demo, I'm going to tune the model quality. So I'm going to try to have a model that is as precise as possible. And precision for object detection is a mix of two things. It's the precision of the cropping, but the precision of the class assignment as well. But there are other things to tune as well. So typically, you may want to tune the model size or the model speed, the training speed to reduce the cost, for example. And all of this, you can tune as long as you can print the metric of your choice with SageMaker model tuning. So let's look more at how it looks in practice. So I have my data. So very simply, the annotations, they're in a JSON-like format that we call a manifest, and so we can superimpose the annotation on top of the pictures to see exactly what we want to achieve. So we have the raw data and the annotation on top of them. So we have both the bounding box and the class label. And so this is the model we want to train. This is a task we want to train. It's actually a multitask model, because we have one task cropping making the bounding box, and another task which is finding the right label. And so as I showed, I have this Python script to do the training loop. As Valerio mentioned, in SageMaker, we can run iteration of arbitrary code in Python or Docker via what we call the training job. And so this is what we have in this first section. We define a job. So I'm going just to choose a prefix. I'm going to define as well metrics. And this is my job definition. And basically that contains the training code. It contains also a Docker image to run that training code on. And it also contains the cluster configuration. So here I'm going to train on a cluster of one machine, a G4DN.16. This is a machine that is good for computer vision because it has a lot of CPU in addition to its GPU. So it has a small T4 GPU, but with 64 vCPUs, and this is plenty of CPU budget to run data loading, augmentation, etc. So this is good for pretty useful for computer vision development. Not the fastest we have, but convenient and pretty agile. And typically, when I execute that cell and when I launch the fit, this launches a task, a remote, a fresh ephemeral virtual machine that will launch my code. So this is one job. This is one task running. It's very similar to running a Slurm job or to running, a task on Kubernetes. Is basically, running my code in a self-contained environment, except that with SageMaker, it's fully managed virtual machine lifecycle. The service creates for you a new machine, and that machine will live exactly for the duration of training. And so this is the entity, the construct that I can tune. And with SageMaker model tuning, you have functions to tune the metric of your choice, to optimize, to tune the parameter of your choice to optimize the metric of your choice. So let's see how it looks like. So I have a class in the Python SDK. I have many classes. I have classes to define parameter ranges, and I have a class to define a tuner. So here, basically, if you saw, my job definition, I don't have much parameter specified. I just specify number of epoch, but in my script, I also define a lot of arbitrary parameters as script arguments, and those are the quantities I want to learn in a programmatic fashion. And so typically in my tuner class, I will define ranges. And so here I have six parameters I want to learn. And so I have the learning rate, which is a pretty frequent, parameter to tune in deep learning. Same thing, with the batch size. I also have a factor. So this is basically to schedule to adjust the learning rate throughout the training. A bit like as human, we learn fast when we're kids and we learn slower and slower as we grow. So neural networks, sometimes they need the same thing. They need, to learn fast in the beginning and then to decay a bit how fast they learn, to capitalize on their knowledge. And so here I'm going to adjust that learning rate factor, weight decay. Specifically to object detection, I have a coefficient to adjust, how much I adjust the importance of class assignment versus bounding box precision. And interestingly, and this shows as well how versatile SageMaker model tuning is, here I decide to tune also the model itself. So my model, it's a detection, Euro 3 detection architecture. But in my deep learning framework, I can choose a backbone, which is a model chunk, basically what transforms the raw data into features. And basically, I'm going to search in the model space. So this is a small space here. I have just two values. I'm going to evaluate, a darknet backbone and a mobile net backbone, which is much smaller. And basically, what I want to show here that SageMaker tuner, but I mean, very little constraint on what you can tune. You can have categories, continuous parameters, integer parameters, and you can get very creative. And so here, in addition to scientific parameters, I'm also tuning the model backbone, and I could tune much more things as well. So this is the parameter I'm going to change, and the service is going to change and to search. And this search is made to maximize or minimize a quantity of your choice. So here the quantity is defined in the tuner class, and we can see in my tuner class, so this is the object that defines the search. So I say which metric I want to minimize or to maximize. The metric are defined here. So again here, full creativity. The metric only has to be a regular expression. When you use custom code, if you use our built-in algorithm, because in SageMaker you also have 20 built-in algorithms, you are more constrained because we write the code, and so the metrics are more limited. But when you use your own code, whether in a custom Docker or in a framework container, you can use the metric of your choice. You can get very creative. It could be precision like here, but it could also be, if you can print it, the training cost, training time, or why not, the memory footprint as well. You can tune anything you can print or log. And so if we take a look at my script, we see here the colleague who authored the code. We see there is a print statement for the map, for the trailing map, and for the best map so far. The map being the mean average precision. And so I'm just going to write a regular expression, which is what SageMaker model tuning expects. A little regular expression here to capture my metric. And so this is what I'm going to tune. So then I define a budget. So I want to test 70 different configurations. So I'm going to launch 70 jobs. And there is a trade-off as well between parallelism and sequentiality. If you run things one by one, you capitalize more on previous jobs, and the tuner can learn optimally. But it's a bit slower, at least in terms of duration. Whereas if you want to go fast, you can configure parallelism, to have more attempts to in parallel. But then the tuner, in the beginning, will launch more jobs at random, and so you may learn less fast. So this one is a trade-off. Here I define a parallelism of 3, and I can also define a name for the whole tuning job. So this is my object configuring the search, and then I can fit it. So this is basically going to launch a long-running process in the SageMaker backend, and this is going to basically launch my search. And this is fully serverless. Once I do this, so we see the code executed, I launched the call, and now I can close my laptop for as long as it needs to run. SageMaker automatic model tuning orchestrator is going to lead that search by itself. So it's going to first run those 3 jobs, and then here I have a Bayesian strategy. And so in the backend, it will fit online a Bayesian model to learn what spaces of the config space are more promising, and to define where to search next. And so this is a very big value added, a very big differentiator compared to pure offline search libraries that you could use on your laptop. Here, this is not a library; it's a service. So yes, it does parameter search, HPO, and the science is very good. But in addition, you have a serverless control plane. The library runs for you. The schedule is defined in the cloud. You don't need to create a machine to run the tuner yourself. You just launch the SDK call, and the tuner will run and live its own life in the cloud. And of course, it will emit plenty of metrics of information for you to track what is happening. So I could go in the SageMaker console, to see the jobs, to see the progress. We also have, the similar information available directly in the Studio interface. So I don't have to leave and go in the SageMaker console. I can check, for example, in the experiment menu. So if I refresh here, I see there is a new experiment happening. I have my 3 jobs, my 3 first jobs. Those 3 jobs I can open in trial components. They are in progress. I can compare them, add if I want to know more metrics. So let's see, for example, what SageMaker is testing first in terms of config. So we can see one is batch 5, batch 3, batch 2, few options in terms of class factor. So all of this, is defined by the scheduler, by the automatic model tuning search engine that is, proposing configuration to try, and then collecting the feedback and then defining new areas to search. And I can click also. I can view the progress. So here, because I launched them a minute ago, I may not have, a lot of metrics to see. If I open them, no data yet. But to show you fully a pretty complete exercise, yesterday I ran a few of them, and so basically I'm going to attach. So this is a nice feature as well. You could use this tuner class for analytics, and so I'm going to attach a previous run to my tuner class, and in one method call, I can fetch all the experiment data in a data frame. So this is cool. Now I can do, for example, df equal to tuner analytics.data frame, and then I can visualize my data frame. And so I'll have all my experiment metadata available in Pandas programmatically. So this is another big value added, compared to offline parameter tuning library that you could find in the open source. Is again, this is not just a library, this is a service. And the service, as I said, it has the serverless scheduler in the cloud, but it also has a metastore. And so you could browse metadata. You don't have, to save the metadata yourself in a laptop or to share with your colleagues. This metadata is in the cloud in a serverless metastore managed by the service team, and you can access it and visualize it, a long time after you launched the experiment. It's actually, a pretty reliable distributed system where those components live their own life and are managed by the SageMaker team. So I have this metastore. I can view, the data, all the past experiments, and I can also, because it's Pandas Python, I can also, do a couple visualizations. So, for example, this is another notebook that we have online at this QR code, this URL on GitHub, and in this notebook, we have a couple, Pandas functions defined to analyze tuning jobs. You can also do diagrams in experiments, or you can also view, charts, time series in CloudWatch. Here I wanted to do something a bit more extensive. I wanted to see all of the jobs overlaid in the same relative time scale, the same place, to see, how long did each job run. And so I'm going to run it all, and we're going to see. And actually I already have, I think, in memory. So yeah, that's that previous experiment with, I think it is 70 or 80 iteration. So this is, we can see here all the metrics that were emitted during my training job, during my training loop. Those metrics were in CloudWatch, and with the SageMaker SDK, I can fetch them, and I have a function, to superimpose them on the same timescale. And so we can see here we have all those iterations. Some of them are shorter. It's not so it's actually because the iterations they train at different speed, because I have some mobile net model, some ResNet backbones, some darknet backbones. So some of them are shorter. When we color by backbone, we see that that's the case. Actually, we have 2 clusters: the ResNet cluster, the darknet cluster, and the mobile net cluster. And here's the mobile net is converging faster. So the best model in red here was using the mobile net backend. So all those stats, you could create your own because we have the raw data in the meta store. You can use it with pandas. It's very easy to create your own chart with your favorite data viz library. And finally, what I wanted to show is that we also have a nice method to get the best model. So I could call tuner best tuning job, and I have here my best job. So this is the name of my best job, and I could call that at any time. I don't need to wait hours or a day for the job to complete. At any time, I can fetch the best job found so far. This job I deployed on SageMaker endpoint, a CPU endpoint, just to show you that we got a good model. So I have here a test picture, and this test picture, we can see it right there. It's a picture with dices. It was not in the training set, and I can send an inference to my endpoint. Took a second or so because this is a CPU endpoint, and we can check when we overlay with the class names. We can check that the model made some good predictions. So this was a quick demo of SageMaker training with custom. With custom metrics and custom code. And this is not limited to MXNet. You could do with your own Docker. You could do with R, with PyTorch, TensorFlow. It's really it's available for any time. So this was basically a quick demo to show you how SageMaker model tuning works on custom code. And this was computer vision example with MXNet. But again, this functionality is completely model agnostic. It's completely metric agnostic. You could use with your own Docker. You could use typically with R, for example, and you could use with our framework images for scikit-learn, XGBoost, PyTorch, TensorFlow. It's really up to you to be creative and to optimize your workflow. And so with that, we're then going to see an even more realistic use case, because this is an actual business use case from our dear customer Sophos, and I'm going to leave the stage to Thomas.
Hi everyone again. In this presentation, I would like to show a use case for SageMaker hyperparameter tuning for one of our running projects, which is classifying the long tail of the internet. Let's go through quickly the agenda of this presentation. In the first section, I will explain why we are doing this project and why are we using machine learning to do it. In the next section, I will explain how it translates to a hyperparameter tuning problem, also the experiment setup that we have for this specific project. And finally, I will show how the hyperparameter tuning actually affects the results. So the motivation for the project is that we believe that the security profile of an organization is partly a function of the URLs that the organization employees browse, and that content can vary widely. So essentially, our goal is to categorize every URL lookup in our customer telemetry, and we want to categorize those URLs into one of 80 categories that we track internally. On this slide, I'm showing 9 categories out of that 80. These URLs being opened could have various impacts on the organization. We are looking here at that impact from 2 aspects. On the x-axis is more from a security impact. So if we look at the low impact sites, that would be from category from trusted update sites, search engines, blogs and forums. So you can imagine a URL from Stack Overflow will be categorized in blogs and forums. A URL from Google will be categorized as search engines. Those pose relatively low risk, while sites hosting pornographic content or selling drugs or hosting intellectual piracy, those sites are simply just infected with malicious content. So there is really no question that we want to differentiate between these set of URLs. And the other aspect is more from the web content filtering view. Then again, we have the low risk category sites. Those are sites that we would need to do our everyday jobs. But for medium sites from this aspect, we have social media sites that can vary organization to organization, whether they want to allow their employees to browse Facebook, for example, during work hours. But for sure, no company would want to allow their employees to browse sites from the categories on the top right and expose themselves to the legal or ethical impact from those sites. So we want to categorize our customer lookups. This process is generally manual, and the customer telemetry is huge. So we need some kind of a strategy to allocate our limited manual resources to gain the most most coverage from the manual effort. There are multiple ways how to label URLs from the telemetry to cover most of the lookups. One of the most straightforward approach to do this is to rank order the domains by popularity, meaning that we take a domain from the URL telemetry and we count how many URLs were hosted on that domain, and we might or might not weight it with the prevalence of that URL. And by this number, we rank order the domains, and we start going down this list and manually label these domains. Now, the good news on this plot is on the x-axis, we can see the number of domains labeled by this strategy, is that if we label roughly 100K URLs, domains, then we gain the 65% coverage in our customer telemetry. So you can imagine if you labeled google.com as search engine, that would cover a pretty big chunk of the customer telemetry. But the bad news this plot delivers is that if we label an additional 1 million domains, then we only gain 5 extra% of coverage in our telemetry. So we can see that the return of investment exponentially decays after a certain point. And not only that, the long tail of the internet is extremely volatile, so it changes frequently. So by the time, if we ever get to the end of the categorizing of the long tail of the internet, we could start over because new domains are registered or domains die out. So it's simply not feasible manually. So the goal of this project is to circumvent the current limitations that we have, that the labeling process of URLs is a manual, slow, and simply just won't scale. We propose a machine learning model. We propose to use a machine learning model, which would act as a pre-filter on every URL lookup that could enqueue URLs for further deeper inspection methods, such as pulling HTMLs from the URL or images to classify. But this first pre-filter model needs to be really lightweight because it will be called on every URL. And we do this to get that remaining 30% in our customer telemetry to understand best of our abilities what's going on in terms of the customer lookups. On this plot here, I'm showing the class distribution of the 80 classes that we track. This highlights two problems. One is obviously that the class distribution is imbalanced, so you can imagine that we have more examples for search engines than the gambling sites or sites trying to sell alcohol or weapons. So the imbalanced classes are one issue that has quite a literature, and the other issue is that we have classes that we have very few training samples for. And to tackle these issues, we introduce three techniques. So formally, the problem is that we have URL input that we have as a ground truth from one of the 80 classes, and we have a model prediction P, and we apply a loss on top of this too, and we want to minimize this loss. So essentially, we want the prediction and the ground truth to be as close as possible. Let's look into what happens for each of our techniques that we apply to this problem. First, we use data augmentation, meaning that on the plot we can see we have our labeled data as a starting point that goes into our model, and we get a prediction. And what we do additionally, we take our unlabeled data and run it through large language models. First, we started with T5 and then went into the GPT-3. And these large language models produce soft labeled data for us, and those also go into our model, and we predict on those too. So initially we had our loss, and then this introduces a new part to the equation. So we have the same loss prediction for those URLs with y hat as soft labels, and it is modulated by a hyperparameter alpha, which roughly translates into how good are the soft labels that we acquired from the large language models. It's an empirical question how how this will improve our training process and results. So this is a hyperparameter that we want to tune. As for the next issue, which is the class imbalance, we picked a paper which is called Class Balance Loss based on effective number of samples. In that paper, the authors argue that there is a common reweighting technique by inverse class frequency that we have on one hand, and the other hand that we obviously don't do anything about the class imbalance. And they say that the best performance is probably achievable in between the two. And they introduce a hyperparameter for this, which we will call beta in this setup. So that introduces a new multiplication to our equation. So you can see in the equation, if you substitute beta out with 0, then it becomes the previous equation, so no reweighting essentially. And if it's very close to 1, it will equal to the inverse class frequency reweighting. So this is again a hyperparameter beta, which will scale between the no reweighting and inverse class frequency reweighting. And finally, we introduced task augmentation, meaning that we have our main task to classify a URL into one of the 80 categories, and we introduce multiple additional tasks. So this URL classification is not something just Sophos wants to solve. So other vendors have categories for URLs too. And what we do is that we take those labels from third-party vendors and we add those to the prediction problem as auxiliary problems. And we take these categories that do not map necessarily one-to-one to our categories. And we optimize that too. And what we expect this to do is to regularize the latent space in a way that it might lead into a better separable space for us to by the shared layers of these different tasks. So if you look at the equation, it has a third part now, the third final path, which is a summation. So J goes 1 to M, which is the number of auxiliary tasks introduced, and it's modulated by a gamma, which will essentially say how much other vendors' predictions should formulate our latent space in the shared layers. So again, this is again empirical question. So on the left, we have our modeling setup, which has the URLs as an input. URLs from these three sources. One source is the set of ground truth labels, the second source is the set of soft labels, and the third set is the URLs with additional labels from other vendors that goes into a Tinybird. We picked Tinybird because we wanted to utilize the pre-training on natural language tasks. So essentially with this model, we want to try to pick out common keywords from URLs, and with the semantic understanding of words, the hope is that site having the keyword gum will be near to a site that has the word knife. And finally, this goes into the optimization problems, the main task, which is a softmax to categorize into one of 80 categories, the URL modulated by alpha and beta, and finally the auxiliary tasks for third-party labels modulated by gamma. And on the right, we have the data setup for our experiment. We use a time split, so the training data is from the start of January 2022 to end of January, and the validation and test data is from roughly start of April to end of April. It's split in two, so 2-week validation, 2-week test data. We hyperparameter tune on the validation data. And one additional remark is that we remove any domains that we have seen in the training data, because we are not interested how well we can memorize domains, but rather how well we can pick up these these category-specific keywords. How does this translate into implementation of SageMaker? Our objective is, in this case, is to maximize the F1 macro score across all classes. We use the Bayesian hyperparameter tuning strategy for hyperparameter tuning jobs to tune the 3 hyperparameters alpha, beta, gamma from a logarithmic scale. It's bound of 40 jobs, traced sequentially, and these are the results we managed to achieve with that. On the left, I'm showing a parallel coordinates plot with 4 columns, which shows the combination of the hyperparameters with regards of the result. So the first column is alpha, then the beta and gamma, and finally we have the test accuracy. So the first note is that the test accuracy range is roughly between 50% and 43%. So the choice of these hyperparameters can heavily influence the results. Second note is that we can see the augmented sample weight is something the Bayesian tuning strategy decided to converge into one. So the quality of our augmented labels are pretty high. The imbalanced weight depends on the other parameters. And finally, it looks like the Bayesian strategy for gamma resulted in a very low weight. So it looks like the other vendors' labels do not have that much. And on the right, we have another view on the same results. So it's the ROC curve for the class of URLs of gambling in a one versus all setup. So the blue curve shows our initial guess, where we picked alpha as 0.5, beta close to 1, gamma 0.1, and the hyperparameter tuning showed that it can be improved greatly. So 10 to the -2, it improved roughly 10%, which in a sense gained us a significant boost in performance. So to conclude the talk, SageMaker hyperparameter tuning can improve the results, not in terms only of the traditional hyperparameters, but by finding the optimal weight for data augmentation or class imbalances or task augmentation. And on this specific 5 million set of samples, with a relatively short training time due to the massive parallelism, it was able to boost our initial guesses for hyperparameters in terms of accuracy with 5% and 10% TPR at 10 to the -2 false positive rate. And with that, I would like to thank you for your attention.